Now we're going to talk about or define the Jacobian. So what the Jacobian is, it's useful when we are applying these transforms and converting between, say, R and G, my image and my pre-image. But the Jacobian measures how much the transformation is expanding or contracting the area around said point UV, right? So UV is in G, the pre-image, and we're going from some image and converting it to maybe a pre-image or vice versa. So the Jacobian, what this does is it gives us the extra factor. It helps us come up with that extra factor. Like when we converted between xy and r theta, between Cartesian and polar, we need that extra factor. And the Jacobian is necessary to help us find that extra factor that we need to use when we are converting. So here you can see the Jacobian defined. So the Jacobian determinant, or just the Jacobian, of some coordinate transformation, x being a function of u and v, y being a function of u and v, is the Jacobian of uv is the determinant of this matrix formed by partial derivatives. So partial of x with u, partial of x with v, partial yu, partial yv. And then that determinant, we just cross multiply and we subtract those two products. And we have some shorthand notation that sometimes students find helpful. It's just partials x, y in the top, and then partials u, v in the bottom. So you see x over u, y over v, and then we reverse them when we subtract y over u, x over v, y over u, x over v. Whatever works to help you memorize or recognize this pattern. X is in the tops, Y's in the bottoms, U's first, V's second. Okay, so let's talk about the substitution, kind of the formula we use for substitution with double integrals. So looking at this, substitution for double integrals. Suppose we have a function xy continuous over its region R. So you've got xy, and we want to convert it. We're going to use substitution to simplify it into something that's in terms of u and v. So G is the pre-image. So in that video before this, we went from the pre-image and we created the image. And the whole point of that was for us to recognize that it would be easier to use it in terms of u and v instead of x and y to integrate. Back to the definition. G is the pre-image of R. Okay, so x is some function g in terms of u and v, y is a function h in terms of u and v. And this is assumed to be one-to-one because remember we talked about these transformations. It could be an inverse when we go from g back to r. So remember we went from g, we transformed it to get something in xy, went from uv to xy, which was some region r, and then the inverse, which is why it has to be one-to-one, takes us back to u and v, which is maybe simpler or more easy for us to deal with. So this transformation is one-to-one on the interior of G. G and H have continuous first partial derivatives within the interior of G. So that double integral over R for my function f of xy dx dy, we can rewrite that as the double integral over G. F instead of x, we have g of uv. Instead of y, we have h of uv times the Jacobian, that's my extra factor, du dv. So it's kind of like converting from rectangular to polar, and we always have that extra r factor in there. And it's important to note here that this is the absolute value of the Jacobian. So scrolling back up, this Jacobian notation doesn't have bars around it. So these bars up here, they don't mean absolute value, they mean find the determinant. But down here in this integral, that's the absolute value of the Jacobian. So we just need to make sure that that extra factor is positive. So let's do an example where we find the Jacobian for some polar coordinate transformation. So we are going to find the Jacobian for this polar coordinate transformation. The transformation is defined by the fact that x is some function of r and theta. We can think about that as u and v. Also, y is a function of r and theta. So once we've done that, we're going to take our Cartesian integral and rewrite it as a polar integral. So this is what the Cartesian integral might look like. And this may be very difficult for us to integrate considering our bounds. So this transformation, turning the x and y's into r cosine theta and r sine theta respectively, that making it this polar integral is going to be simplify the calculation. Okay, so in order to make the transformation, we need to find the Jacobian. So step one, part A here, let's find our Jacobian. And the Jacobian in terms of r and theta is partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta, which is going to be the determinant of this matrix, partial derivative of x with respect to r, that means cosine theta is a coefficient or a constant, so I've got cosine theta. X with respect to theta, that means r is a constant, so I have negative r sine theta. Y with respect to r, that means sine theta is a constant. And then y with respect to theta is going to be r cosine theta. All right, so this is how I get my determinant matrix set up, and my Jacobian here in terms of r and theta is going to be r cosine squared theta minus negative r sine squared theta, or r cosine squared theta plus r sine squared theta, which cosine squared theta plus sine squared theta is 1. So we end up with the Jacobian is just r. You see now, remember I said the Jacobian is that extra factor. Kind of makes sense, especially when we have something very basic as what is listed here. I mean, these are the definition of polar coordinates. So it should make sense that the extra factor found by the Jacobian is that r value. So for the second portion here, assuming that we originally had some integral over the region R of something, Cartesian function, f of x, y, and we wanted to rewrite it now using our transformation that created it over some region G. So we're kind of simplifying the shape of the region so that it's easier to integrate. That's the whole point of this. Well, that would become a function. The x becomes r cosine theta. The y value becomes r sine theta. We multiply by the absolute value of the Jacobian, r, which r is positive. And then we have our integrating factors, dr d theta. So this would be how we would rewrite it. Okay, now we weren't given an original function or original bounds that needed to be changed, but this is how we would apply using that Jacobian in order to transform it. So a little bit more visually, we have G, and these function transformations transform G into R. This Jacobian factor, R here, which we calculated, that scales the differential rectangle dr d theta in G to match with the differential area element dx dy or dy dx in R. So this Jacobian scales that transformation. All right, so maybe I hope that helps, it makes sense to you a little bit more. As always, email me if you have any comments, questions, concerns. We have one more example video in this long video series coming right up. See you in a couple seconds.